Hi everyone, good evening. Welcome to week 6 of problem solving sessions for probability for computer science course. Okay, week 6. My name is Bhavya. I'm a PMR scholar at IITM. And this is the sixth lecture, and we are having these sessions every Tuesday, 6 p.m. to 8 p.m. Okay, so last week, what did we see? Last week, we did mostly Markov chains. Okay, things like what is a Markov chain, applications, stationary distribution, which was a very important concept. Okay, formula for stationary distribution and so on. So this is what we did last time, right? Solved lots of problems. One problem we left as an exercise at the end, so that we'll solve in the beginning of this session, which brings me to this week's content. That is again Markov chain. Okay, that is again Markov chain, but this time we are dealing with um, something called ergodicity and Pagerank, and it had this cell genetics also, but it deals with very specific kind of formulas. If you watch the lectures, then it won't be a problem for you. Okay, so we'll do like about one question on this. Okay, that's all. And okay, and the other topic is let's see what, oh, sampling is a very important concept. Okay, it's very practical, very useful concept called sampling. Okay, so we'll be looking at problems from this. So before we move on to problems of this week, we'll first solve the problem that I left for you guys last week. Okay, this one. Let me copy it. Sir, copy and delete. No. Okay. So let me first repeat the question, then I'll ask if anyone has solved it or got some ideas. Okay. So let me repeat it once. I have four umbrellas. Some are at home, some in office. Okay. By the way, this is a question on Markov chains. Okay. So you need to use Markov chain somewhere. Okay. I have four umbrellas. Some are at home, some in the office. I keep moving between home and office. Okay. Every day I go to the office and then I return home, go to the office, return home. But the thing is, I take an umbrella with me only if it rains. Okay. I take an umbrella with me only if it rains. If it does not rain, then I'll leave the umbrella behind at home or in office. Okay. For example, let's say I'm at home and I have two umbrellas. Okay. For example, oh, Kishore is also here. Hi, Kishore. I have two umbrellas. Okay. So, which means since I have a total of two umbrellas, I have two more umbrellas in the office. Okay. And the scenario is it rains. Okay. And then I need to take an umbrella, right? Because I don't want to get wet. So I have taken the umbrellas and I am at the office. Now it does not rain, let's say. It's sunny. Okay. And I go back. I go back without an umbrella. So I just have one umbrella. And there are three umbrellas here. Now what I do is, let's say I go to the office and it rains again this time. So what do I have here? No umbrellas, zero umbrellas. And I take that umbrella with me and it rains. Okay, and I'm at the office now, right? Now I go back, let's say, and it's sunny again. So I don't take an umbrella. So I'm back at the scenario where there are zero umbrellas. Now, let's say I go to the office and it rains. But I don't have any umbrella, right? So I need to travel without an umbrella. So what do I happens to me? I get wet because all the umbrellas were at the office only. Okay, I hope the scenario is clear. So I take the umbrella only if it is raining, and if it so happens that I'm at home and all my umbrella are at the office and it rains, or I'm at the office and all the four umbrellas are at home and it rains, I'm going to get wet. Okay, so that is what this last line says. Okay, so the question is, if the probability of rain is p, what is the probability that I get wet? But before this question comes in, we want to model this as a Markov chain, as states and then probabilities of moving to other states and so on, right? So, did any of you guys try this problem? I just want to ask before I move on to solving it and into modeling this into a Markov chain, or if you have any ideas in how to make the Markov chain.
So I did not try it, but then
Okay.
I guess that there would be in total 10 states, like say 5 corresponding to that home with no umbrella, home
Okay.
with one umbrella,
Okay.
and then so. And similarly, I would be having 5 more states for the office with no umbrella, and then office with 4 umbrellas. And then we can define the transitions depending upon whether it's raining or it is sunshine,
Okay.
and then we can decide the probabilities, and moreover we can designate some of the states as the states wherein the person is going to be affected by the rain. Yeah.
So inside the home states, what are the states?
So there are 5, like say home and having 0 umbrella,
Hmm.
and home having 1 umbrella, and 2, and then 3, and then 4.
Okay, good. And
Similarly
office
for
has
office are
similarly.
5.
Right?
And now, yeah,
Yes.
yes.
Good.
And now we can have the transitions among these states, like if corresponding to four home,
Huh.
and if it rains.
Yes.
So, like say corresponding to 0 home, and if it rains,
Huh.
then the person is going to be, yeah, affected.
Okay, good. Okay, okay. And when he goes to the office, and let's say he's at zero, when he goes to the office, right?
Yes.
Um,
Then he will go to the state number 4, because all the 4
because
umbrellas
all
there.
the
There.
four umbrellas are there. Very good.
Yes.
And with what probability?
But the probability thing is that now the probability needs to be calculated, because there are 4 umbrellas, and what is the probability of having all the 4 umbrellas? Because the probability of getting this wet is p. So
Oh,
therefore,
no, no.
this will,
P is not the probability of getting wet. P is the probability of raining, on any day.
oh, p is the probability of raining. All
So
right, all
so
right.
so let's okay. State zero is a bit tricky. Okay, let's do state one. Okay,
Yes,
okay. State one. I need to go to the office. Which state do I go to?
yes. So if I go to from the state number 1, then 3 umbrellas there are there at the
Good.
office. So I will make a move from 1 to 4 then.
1 to 4. But 1 to 4 means you've taken the umbrella, no? To
I have
office.
taken the umbrella. Yes, yes,
To
yes.
yes. So you've taken the
So,
umbrella
so,
to
so yes,
office.
there could be, yes. So because the person will take the umbrella only if it rains.
Good.
So therefore, we'll make a transition from 1 to 4.
Okay. With what probability?
Yes, with the probability of p.
Good. Very good.
Yes,
And
and
he need not take the umbrella also, right?
so in that case, the person is going to become, yes. So there should be one more state wherein But then he will definitely take the umbrella along, and there is only one possibility when he does not have the umbrella. He is at home and is not having umbrella. He does not have option. He does not have he does not have option not to carry it. No, no, no.
Oh, no, no, no. That's what he is not going. He's not going to carry the umbrella if it is not raining. Okay.
Oh
See,
yes,
yes. If it does not rain, I leave the umbrella behind.
yes. So in that case, with the probability of 1 minus p, if with the probability of 1 minus p, the from 1 it will make the transition to 1 to 3.
Good. 1 minus
Uh,
p,
yes,
right?
yes, yes,
And similarly for others, right?
yes, yes, right.
Is Goel's idea clear? I mean, I'll build on it. Okay, but is this idea clear? So what Goel is saying is, I'm going to. Okay, Ankita is saying. Others also let me know. Okay, I'm going to make these states. Each state corresponds to the number of umbrellas, and I'm dividing the states into two types: the home states and the office state. And further, they are labeled by the number of umbrellas. Okay, so each state I represents. Okay, that's very bad handwriting. Represents I many umbrellas. Okay, and so if I am at state 1, it means I'm inside home. Okay, let me rename them. So okay, so this will become H0, H1, H2, H3, H4. So these represent home states, and O0, O1, O2, O3, O4 represent office states. Okay, so each state HI represents I many umbrellas at home, and similarly for office. So if I am at H1 state, it means I am at home and I have one umbrella at home. It rains with a probability P. So when I need to go to the office, let's say it rains. So with probability P, because I know that if it rains, I definitely need to carry an umbrella. So with probability P, I'm going to go to state O4. Why? Because I have taken the umbrella to office and there are now four umbrellas because I've taken the umbrella. And if let's say I'm at H1 only, okay, which means that one umbrella at home, which means at office I have three umbrellas, and the remaining three are at office, and it does not rain with what probability? 1 minus p. So with 1 minus p probability, I do not take the umbrella and go to the office. Okay, and to how many umbrellas in the office? I have not taken the umbrella, so the three umbrellas stay in the office. Similarly, if I'm at H2, okay, similarly if I'm at H2, I'm at home with two umbrellas. Okay, I'm at home with two umbrellas. If I'm at home with two umbrellas, it means in the office there are two umbrellas, right? So if it does not rain, then it all well and good, because if it does not rain, then I'm going to not take an umbrella and go to office where there are two umbrellas, okay, with 1 minus p probability. But if it rains, what state am I going to go to? If it rains and I need to go to the office, I need to take an umbrella.
O3.
Yes, O3. With what probability? P probability, because with P probability it rains, right? And okay, similarly, I'm at H3 and it rains. Which state am I going to move to?
So with the probability P, I would be making the transition to the state wherein the sum of the indexes came out to be 5. And with the probability of 1 minus P, I would be making the transitions to the states wherein the sum of the subscripts or the indices is equal to a 4.
Sure. Wait, no. See, when you are H3, the logic is still same. When you are at H3, if you take an umbrella, if it rains, you take an umbrella, so you move
Then I
to
O2, and
O2.
the sum came out to be 3 plus 2 is equal to 5 with the probability of P. So I was talking about the sum of the indexes. I mean the subscripts here, like ranging from 0 to 4.
Oh, okay. Yes. Some of the
In that
that's a
sense.
general way to do it. Yes. But I'll come to that. Okay, good. Okay. So then, if you are H3 and you take no, so if you are H3, you take an umbrella, so you move to O4 with probability P. And if you don't take an umbrella, then you. Oh, sorry, what am I saying? There were
Cannot be O4.
one umbrella,
Cannot
so
be
you need to
O4.
move to O2.
O2 with the probability of P, 3 plus 2, 5.
Yes, 3 plus 2, 5.
Yes. And with the probability of 1 minus P, I would be making move to the state wherein the sum came out to be 4. So it has to be O1 and need not
Yes,
to develop the logic, I guess.
yes, good. Nice, good generalization. Okay, so, and I hope the logic is clear. So, is everyone fine with this? Yeah, Kishore.
See, probably I might have missed the initial part
Hmm.
as I joined a bit late.
Sure,
So,
no
see,
problem.
to some extent, to some transitions, I got the point. See, let us suppose if we take H3
Hmm.
with 1 minus P probability, uh, no, with P probability, what we do is we go for O2.
Hmm.
Okay. So, but when it is 1 minus P probability, uh,
So,
we are
so
going to O1.
you are talking about which state? H3, no? Okay.
H3, yeah.
Yes.
So, so
So,
what is the basic? What is it?
yes. I'm going to reinterpret it again. Okay, that's fine.
Okay.
Okay. So H3 means I'm at home with three umbrellas. Okay,
Yeah.
means I'm at home with three umbrellas. And if I have three umbrellas at home, and total there are four umbrellas. So how many umbrellas are at the office? 4 minus 3, 1. Right. The remaining one umbrella is in the office. That was clear,
No.
no?
How is 4?
Because the question itself says I have four umbrellas. Some are at home, some in office. So if three umbrellas are at home, the remaining one is in the office.
Okay.
Okay.
Yeah, but I have 4 umbrellas, some at home, some in office. But this doesn't satisfy with the transition with H3 to O2, right?
Yeah. I'll come to that. So why O2? I'll come to that. So I'm at H3. In the office, there is one umbrella. That much, right? Is clear, right?
Okay.
That much
Yeah.
is clear, right? Now, if it does not rain, okay. So okay. So what point did you make? Okay, yeah. So if it does not rain, it does not rain with probability. It rains with probability P. It does not rain with probability 1 minus P. Okay. If it
Right.
does not rain, I'm not going to take the umbrella to office. I'm not going to take any of the three umbrellas to office. So when I reach the office, how many umbrellas will I see? One umbrella only, because there were one umbrella already in the office, and I have not taken any more umbrellas to the office. No, is that clear, Kishore? So
Yeah.
it
1 minus P probability that satisfies.
yes, one
What
minus
about
probability. I'm going to be in office with one umbrella, right? Office will with 1
yeah?
minus P probability. I'm going to go to the office with one umbrella, right? Now, if it
And
rains, yeah,
right.
yeah. Now, if it rains, okay, if it rains and I'm at H3, I need to take an umbrella in order to not get wet because that's what the question says. Okay, I take an umbrella with me only if it rains. Okay, So now let's say it rains. With what probability will it rain? With P probability. If it rains, I'm going to take an umbrella. So there are total 3 umbrellas. Now it will be 2 umbrellas. No. Now you are going to take an umbrella. In the office, there was one umbrella there. I've taken one umbrella. So in the office, total how many umbrellas will be there? 2 umbrellas. No.
Is it now pointing to H3 with probability P pointing to O1 or O2?
O2. Because with P probability it rains, and from H3 I've taken an umbrella to an office which already had one umbrella. So I've brought one more umbrella, right? So there will be O2 because there are 2 umbrellas in the office.
Yeah, two here two. When it transition happens, at home it would remain 2 umbrellas, and then at office it would be 3 umbrellas. After transition happened.
Oh, okay. After which point? Which point? From where are you going? From where are you starting?
H3 to O2.
Okay, H3 to O2 is H3 means you have 3 umbrellas at home. Now with
Right.
P probability it rains, which means you've taken an umbrella, and you need there were one umbrella at the office already. Okay, so now the total number of umbrellas at the office 4. Right?
But see, O2 state of O2, it has 2 umbrellas, right? Based on that.
Yeah, now it has 2 umbrellas because you've taken an umbrella.
No. Basically, based on the state itself, the count of umbrellas would depend, right?
Yes. For example, if I'm in
O3,
state O2,
when we say H3, when we say H3, it has 3 umbrellas, and when we say O2, it should have 2 umbrellas.
yes, H3 means 3 umbrellas at home, and O2
So
means
thereafter,
2 umbrellas at
when
home.
we transition, right, with probability P,
Yes.
so the O2 will be the count of umbrellas in O2 becomes 3, right? Because it brings one umbrella to O2 state, and then adding plus 2 with 1, it becomes 3.
No, because we've already added now. Because see, you're at H3 right now. Okay, which means at home you have 3 umbrellas, and total there are 4 umbrellas, which means there is one umbrella in the office. No. Now you've taken an umbrella, so now you land up at O2.
Okay,
You
got
don't
it.
add
So,
more to it.
okay, so altogether, what we need to take is 4
Yes.
at the max.
4 umbrellas, right? Total there are 4 umbrellas. Okay, all is clear. Okay, great. So similarly, just to for completeness, okay. For example, if I start at H4, how many umbrellas do I have? 4 umbrellas. All of the 4 are at home. Now, let's say I need to go to the office. So, and it rains. With what probability does it rain? P probability. Then I need to take an umbrella, right? But how many umbrellas are at the office? All the umbrellas are at home. So at the office there are 0 umbrellas. So when I take an umbrella to the office, how many umbrellas are there in the office now? One umbrella, right? So H4 to O1 with probability P, because with probability P it rains, and therefore with probability P I take an umbrella. If it does not rain though, so with what probability? 1 minus P. If it does not rain, then what happens? I don't take an umbrella, right? So therefore I move to O0 with probability 1 minus P. Okay, because I don't take an umbrella, so the office still has 0 umbrellas. Kishore, is that fine? Okay, great. So Harshul, Shovan, Rajnish, you guys fine?
Yes, fine.
Okay, good. Okay. Shovan? Okay.
Yes, sir.
Harshul? All good?
Yes.
Okay, good. Okay, so why I'm asking is because now we are going to take it to the next level. Okay, so notice that we can make this simpler. Okay, we can make this simpler Because like Goel suggested, we can partition it to home and office. What I'm saying is now that you don't even need to partition it into home and office. At any point of time, you are either at home or at office. Okay. So you can compress this entire thing into 5 states only. The current state just represents where you are. It need not represent whether you are at home or you are at office. Okay. So I just have the states now 0, 1, 2, 3, 4. Only 5 states. Okay. State I represents wherever I am, either home or office, I have I many umbrellas. Okay. Wherever I am, either home or office, I have I many umbrellas. And this logic still works. So I have, say, 0, 1, 2, 3, 4. Okay. These are the states. So it does not, the thing is, it does not matter. Okay. Now I'll show you why. So for example, let's say I am 0. The best way to see it is like I'm at place A or place B. It does not matter whether B is A or B is. So it does not matter whether home is A or home is B and so on. I'm at a place where there are 0 umbrellas. Okay. Oh, okay. Let's start with 1 actually. I'm at a place where there are 1 umbrellas. It's actually simpler if I order them as 0, 4, 1, 3, 2. Okay. 0, 4, 1, 3, 2. The diagram is clear. Okay. So I'm at a place where there is 1 umbrellas. So the other place, for example, I'm at home, then the other place is office, or if I'm at office, the other place is home. I'm at a place where there are 1 umbrellas. The other place has how many umbrellas? 4 minus 1, 3 umbrellas, right? So I go to the other place. Okay. I go to the other place, which has say 3 umbrellas, and and if it rains, then the other place the number of umbrellas increases by 1, which is 4. So when do I take the umbrella? When it rains, which happens with probability P. Okay. And if it does not rain, then I don't take the umbrella, and the other place still has 3 umbrellas. So with 1 minus P probability, I go to 3. So let me, instead of writing 1 minus P several times, let me write it as Q. Okay. And similarly, let's say I start from 3. Okay. I'm at a place 3. If it rains, okay, the other, what does it mean? The other place I have 3, which means I'm at a place where there are 3 umbrellas. The other place has 1 umbrella. If it rains, then I'm going to take an umbrella to the other place which has 1 umbrella. So which means there will be 2 umbrellas. But if it rains, so it rains with probability. If it does not rain, then I don't take an umbrella. So I go to the place which has, the other place which has just 1 umbrella, and I don't take an umbrella with probability Q. Right? Because Q is the probability with which it does not rain. Now, let's say for 2, can you tell me for 2?
So for 2, if it rains, then I will go to 3. And if it does not rain, then I will remain on 2 only. I mean, that 4 and 5 principle is still valid here.
Yes. Good.
And similarly for 4, if it rains, then I will make a move to 1. And if it does not rain, then I will, then I will make a move to 0. Yeah.
Yes.
P and
because
then 1 minus P, yeah, 0. And then from 0, see, not Q, but okay, Q, fine. And from 0, if it does not rain, then I will move to this 4. And if it rains, uh, 0 is trickier, as you said. If it rains, then I will. I mean, this is the position which needs to be examined. Actually,
yeah.
this is the point wherein I'm getting affected by the rain. Yeah.
But don't worry about getting wet or not. Okay, that's why you are saying it. It's the point where you need to. That is right. I agree. But don't get don't think of that wet condition and so on.
Okay, so if
Regardless of whether it rains or whether it does not rain, I need to go
I
to the
will,
office, right?
yes, I need to. I mean, I will move to the 4 only.
Yes. So with probability P, you'll be moving to 4, right?
Yes,
So, but regardless of whether it rains or does not rain, I'll be moving to 4, which means with 100% probability, I'll be moving to 4.
correct. So this will become 1.
1. So this is my Markov chain. Right? Now you have a much simpler Markov chain. Right? So, are you guys fine with it? This is, yeah, there is a conceptual build up here. So I can understand if there is, you know, some problems understanding, but just let me know. Okay, Ankita, this is fine. Okay, good. Okay, Shovan, am I audible? Usually Shovan is very active.
Sir, yes,
Oh.
sir, you are audible, but there was some internet connection beforehand, so
Oh,
I
no,
just
okay.
missed some of the previous part.
Oh, okay. Are you getting this part? Because this is the main. We are going to work with this Markov chain only from now. The previous was to just for a conceptual build-up. Is this clear, or should I re-explain?
Sir, can you just shortly re-explain only the diagram part? I know the Markov chain part. Please.
Huh. Sure. I'll just quickly explain to you. Each state represents where you are currently at and how many umbrellas there are there. Okay, where there are. So the premise is that there are 4 umbrellas in total. I'm at home or at office. If it rains, I'm definitely going to take an umbrella. Okay, to the other place. If I start at home, I need to go to the office with an umbrella. If it rains, okay, and vice versa. If it does not rain, I don't take an umbrella. It rains with probability P. It does not rain with probability 1 minus P, which I'm renaming at Q. Okay. Now, for example, if I'm at state 1, it means wherever I'm currently, there are 1 umbrellas. There is 1 umbrella. Either home or office, it does not matter. There is 1 umbrella. But it means that the other place, for example, if this is the condition that I'm at home, the other place, which is the office, has 3 umbrellas because out of the 4 umbrellas, the other 3 are in the office because 1 is at home. So whenever I go to the office, I go to the office when it's either raining or not raining. It rains with the probability P. So if it rains with the probability P, I need to take this 1 umbrella with me to office where there are 3 umbrellas. So when I take this 1 umbrella to the office which has 3 umbrellas, the total number of umbrellas in the office is 4. With what probability? P, because P is the probability which will rain, and therefore P is the probability with which I will take an umbrella. However, if there is 1 umbrella where I'm currently at, and it does not rain, which is the probability Q, then no need to take this umbrella, right? And the other place, which is the office in this case, okay, had 3 umbrellas, but I did not take any umbrellas. So I go to the office which already had 3 umbrellas, and I don't take an umbrella, so the total number of umbrellas in that place is still 3. So now the current place I am at is the office, but it does not matter where I am. It just matters that wherever I am, there are 3 umbrellas. Now I can just view the Markov chain from here. Okay. And similarly, 3 umbrellas. I'm at a place which has 3 umbrellas. So the other place has 1 umbrella, right? So I need to go to the other place. If it rains, then I need to take that umbrella to the other place. But the other place had 1 umbrella. So 1 plus 1 is 2. right? Now the new place has 2 umbrellas, right? Now, let's say I was at 3, it did not rain. I was at 3, it did not rain. Then the other place has just 1 umbrella, right? 4 minus 3 is 1. And it did not rain with probability Q. I go to the state where I did not take any more umbrellas. So now the new place that I am at still has 1 umbrella. Is that clear, Shovan? So that is the logic.
Yes, sir. Clear, sir.
Okay, great.
Thank you, sir.
Okay, sure. So now we try to solve the question. The question says, if the probability of rain is P, what is the probability that I get wet? Okay, if the probability is P, what is the probability that I get wet? So can anyone tell me, like, how can I examine the probability? When observing the Markov chain, when do I get wet?
Is this probability we are expected to find for the whole chain?
Yes. But okay, for now you need not examine the chain. I'll come. That's a very good point. Okay. That's a very good
But
point.
for right now, one transition you are asking.
So let me ask in this fashion that forget about the Markov chain. Look at this umbrella no umbrella context. Okay, I could be either at home or at office. What is the event when I will get wet? Under what circumstances will I get wet?
So what is the
Yeah, go ahead.
yeah, sorry. So the probability that I am there at the state 0 would be, say, Q plus P square Q plus what should I write? So I need to calculate this. I mean, what is the probability of there at the
Okay.
state 0? And
Okay.
then when I make a move to the state number 4, this is the only possibility wherein I'm getting affected.
Yes. Okay.
So, but then what is the probability of, probability of me to be there at the state 0? So that would be probably the one possibility could be that from 0 to 4, and then I made a move from 4 to Q. This is one probability.
Okay.
Right, but no, 0 to
don't forget about the Markov chain for now. Just what is the event in which I'll get wet?
So during the transition from 0 to 4 is the only thing wherein I'm going to
No, yeah, but forget about the Markov chain. Tell me about the events. Like
So
whether it rains, it does not rain, how many
yes,
umbrellas do I have?
oh, I see. So if it rains, and then I move from 0 to 4.
That's what I'm saying. Don't say 0, 4, and so on.
No,
Tell
exactly to say when it rains and we don't have umbrella,
Yes.
that time we will.
Yes. So
That is 100% probability will be 1
no.
for probability of getting wet.
Yeah. It's no. 100% probability. Yeah. That's when 100% probability you will get wet. That's right. Yeah.
I mean probability of getting wet is equal to 1.
No. That is not true. Right? Goel, is this clear? Right? I mean, yeah, of course this is clear. But right? So, but no rain and no umbrella and rain are independent events, no? So I can multiply these together. Okay. Yes, Goel, now you can apply the Markov chain.
I think it's no rain. Might be probability of no rain.
No, you'll only get wet if it rains.
No, but is it the probability of getting wet when it would be is without umbrella and without rain, right?
No, probability of getting wet is the probability that you have no umbrella and
Oh,
it rains.
sorry.
Yeah.
Probability of getting wet you are asking. That's okay. Then that's
Yeah.
fine.
Yes, Ankita, can you tell me? Yeah. Okay, you are unmuted, but I cannot still. I can't hear you. Are others able to hear?
No, she is not audible.
No, sir.
Okay, Ankita, you are not audible. Okay, yeah, can you use the chat then? Oh, okay. Maybe you were you raising your hand? You're still raising your hand. That's why I asked you. Okay, now it's on. Okay, so that hand raise was by accident, Ankita. Okay, there are total 5 states. Okay. There are total 5 states. Then the probability of having zero umbrella will be 1/5. No. See, this is a Markov chain, remember. So the probabilities are more complex. But that's a good update. So this is what you want to attack, right, Ankita? So this is what you are saying. This is 1/5 times probability that it wins. But then another question is, why did we go through the process of building the Markov chain? So there should be something, right, to do with the Markov chain. And it's not that the probability that each of this is 1/5, because some of these states have a higher probability of landing into, and some of these states have a lower probability of landing into. So here's a hint I'll give you. Long-term probability. As I run the Markov chain, what do you call the long-term probability of entering these states for a Markov chain? So this is my hint to you. Yeah, Kishore?
So maybe when we say the probability of no umbrella and probability of rain, event might be like with umbrella or without umbrella. It's so no umbrella. So we can take it as off of the percentage 1/2. Less and probability of rain and not raining. So it also 1/2 into 1/2 I can say. So altogether 1/4.
No. Okay, probability of rain, by the way, is already P, right? So we have this probability of no umbrella.
Okay.
So this
Raining.
probability of no umbrella is more nuanced. But what I do agree is, right, that this is probability that Markov chain, let me call it M enters state 0, right? This is same as no umbrella, M being in state 0, right? So now that's what I'm telling you. But what is the probability that M enters state 0? Now it's about long-term probability. As you run the Markov chain, what happens about distributions?
So the thing is, the probability of M enters into the state 0 would be, what is the probability that M enters into the state 4, and then from the 4 I make a transition to Q. I mean, this will not depend on the state 1, 3, and then 2.
Okay, but then this now you need to compute what is the probability that you enter state 4. Then
Yeah,
will be like,
so that will depend on, because then I need to compute. I mean, because quite possible that I may keep on moving from 4 to 1, 1 to 4, 4 to 1, 1 to 4 infinitely, and then finally I make a jump from 4 to 0.
Yes, that's right.
So how to avoid? I mean, because this will, I keep on getting a diminished value, and I keep on multiplying, say, p with p square, and then p raised to the power 4,
Yes.
and so on. And yeah,
But that's a good point. So what Goel is saying is he'll do p, then p raised to the power 4, and then p raised to the, and you'll keep multiplying it, then p to the 100 and so on, and then try to compute the probability of entering states. Wasn't there a easier way to do this? Like in Markov chain, we talked about powering last time. No? So we said that, Markov chains, when you keep multiplying them, they sort
So,
of repeat, yeah?
so on what basis we are powering it? The probability we are powering. Is it something,
Yeah,
the first stage it is?
So P4 means you are running the Markov chain for four steps. P100 means you run the Markov chain for 100 steps, and so on. Right? The probability of entering the states on 100 steps. But okay, should I reveal it, or you guys want to think about it? There is one measure, not a measure, I would say, but one important property about Markov chains.
so yes, I mean, in the last session you discussed something about the stationary thing. The
Yes.
distribution becomes stationary, but
Yes.
then that point there itself was not that clear to me. That how is that possible that m raised to the power n becomes equals to 1? Yeah.
Huh? And raised to the, oh,
Something. I mean, you showed something by that m raised to the power n was became stationary and was not changing further.
yes, exactly. So what is it? So let me just do a digression box here. So stationary distribution is the distribution so that no matter what distribution you begin with, for all distribution, which is a vector, okay, of distributions, right? V times the Markov the probability matrix of the Markov distribution, right? This is a matrix, n cross n, will give you the same distribution. And we discussed in the previous session, right? That so this distribution is never going to change. Okay, so sorry, not for all. It's that distribution, but it does not matter from which distribution you started. It does not matter which distribution you started. Eventually, you land up into the stationary distribution. This is for special Markov chains, but we said that okay, that exists for nicely behaved Markov chains. And this, whatever you get, this distribution is the long-term behavior of the system of entering that that those states, because now it means that if it means that this is the long-term behavior, right? Because multiplying with this matrix represent doing one step walk of that Markov chain. And it means that no matter now, if you do v times p to the 100,000, it doesn't matter. You're going to get the same distribution, which means what is the distribution looks like? It looks like 0.5, 0.2, 0.3, 0.0. Okay, it looks something like this. This means the probability of entering the state at 0 at any point is 0.5. Probability of entering state at state 1 at any point of time is 0.2. Probability of entering state 2 at any time is 0.3, and probability of entering.
So I have a query here that if I design the transition matrix, say PM, then what is the guarantee that such a vector B would always exist? And such a stationary distribution, or such a, I mean,
yes,
such
that's what we were saying last time, that your stationary the Markov chain needs to be okay, this is done in this time's lecture, that it needs to be ergodic, which means it needs to be aperiodic, and it needs to be regular. And the question here, it's, don't worry, it's aperiodic regular. So if you recall, I said Regular means that the underlying graph needs to be connected, strongly connected. Every state should be reachable with another state. Aperiodic means there is no, repetition of the states. The set of states over the same period of time repeats over and over again. So Markov chain is there in a loop that is periodic. So it should not be periodic. But okay, so that is a digression. Okay, let's not go for that for now. Okay, but
yeah,
yeah.
but then this is interesting that probably you mean to say that I mean this property will hold true only if the transition matrix is following this property of ergodicity.
Yes,
This is
ergodicity. Yes.
oh all right.
But yeah, I'll talk about that. Don't worry. But let's
Okay.
for now assume that the stationary distribution always exists.
Oh, I see. All right.
Okay.
Fine.
Let's assume that. Okay. So right. Okay. Well. Okay.
Yes,
So
yes.
now, so probability that M enters state 0 is the first entry in the stationary distribution. Let me call it V or pi. Right? Because pi is a distribution. So like the summation of we did it last week.
What did you say per pi? What did you say? How to pronounce this? You
this
wrote
no, I wrote pi vector, this arrow. That's all.
okay.
Pi only.
Okay.
Yeah.
Fine.
So if you remember right, we said pi 1, pi 2, and so on. No? Okay, no one remembers. Okay. We did this solving of simultaneous equations.
Yes.
Right? We did this fact, no? That so maybe because I wrote V, let me write pi. Pi times PM is pi.
Pi 0.
Sorry, yeah, pi 0. Yes, thanks. 0, 1, and so on till n minus. I mean, in this case, it's 4, right? And this represents the probability that I enter state 0, right? Over a long period of time. Okay, so this is what I need to compute. Okay, but okay, so now okay, but I'll quickly tell you because we are running out of time. I'll quickly tell you directly what. And so what do you need to do? You need to compute pi p equals pi, right? And what is pi? Pi is of course pi 0, pi 1, pi 2, and so on till pi 3, pi 4 times the matrix, the matrix of the Markov chain, which is for example 0 moves to 1, 0 moves to 4 with probability 1, 0, 1, 3, and 0 moves to okay, nothing, right? And 1 moves to 3 with probability Q and 4 with probability P. And 2 moves to itself with Q and 3 with P. And right, we did this exercise, no? Converting a Markov diagram into matrix, right? So and 3 moves to 2 with probability P and 1 with probability Q. And finally, 4 moves to 1 with probability P and Q with probability 0. 0 with probability Q. This is what we get. No? And equals same thing, pi 1, pi 2, pi 0, pi 1, pi 4 transpose. Okay. And how did we do it? We did a simultaneous equation. Okay. And so you can try getting this form, but finally what you get is solving simultaneous and simplifying. You get pi 2 equals pi 3 equals pi 1 equals pi 4. Okay. Let me write it as pi 1 equals pi 2 equals pi 3 equals pi 4. Okay. And pi 0 equals q times pi. Okay.
That is not clear to me. Can you show the previous slide to me?
Yes.
I mean, how did we reach till here? And how did we construct this matrix?
So you make the simultaneous equations, no? So you get pi 4 equals the first pi 0. So what you do is, see, you, oh sorry, q pi 0. So what you do is you do simple matrix multiplication, right? So how do you get the first element in the vector? You do simple matrix multiplication. This times this, which will be 0 times this entire thing, and pi 4 times q, right? Sorry, it's pi 4 times q is the first element in the matrix.
Right. Yes, I
Okay.
understood. Yeah. Thanks.
And then
Yeah.
you multiply this with this, and then you'll get q3 q times pi 3, and pi 4 times pi p is q2, and so on. So you'll get some simultaneous equations, and on simplifying you get this and this.
Yes.
And furthermore, like we did this last time, that the summation over all the pi i's equals 1, right? 0 to 3, sorry, 0 to 4. So can you simplify this? Can you bring it into one term? Can you use this? So what does this mean? This means that so using this, okay, this is 1, this is 2, this is 3. Using 3, we get pi 1 plus pi 2 plus pi 3 plus pi 4 plus pi 0 is equal to 1. But what are all these? The pi 1, pi 2, pi 3, pi 4 are equal, no? So you have
Sir, getting pi 4 as 1 by 4 plus q.
we get pi 4 as
1 by 4 plus q.
1 by 4 plus q. That's correct. Yes, good. Okay. So you just make all of these. So let me just write it for completeness. Okay. So you have these are all pi 4s, right? So you have 4 times pi 4 plus pi 0. But what is pi 0? Q pi 4. Okay, and that's how you get this. And okay, good. So therefore, what do you have? Now can you, but what do you need now? What do you need? You need pi 0, right? So what is pi 0? You have pi 4, then what is pi 0?
Q by 4 plus q.
Yes, pi 0 is q times pi 4, which is q by 4 plus q. No? Okay, so this is pi 0. Now, yes, so this is your answer, okay, if it's p. But let's do it. Let's do a practical validation. Oh, sorry, this is not the final answer. So the final answer, probability of getting wet, is that you are
Sir, multiplied by p.
Yes, multiplied with p. That is, you were at so probability that you are at
Kept getting
state
going.
0. Yes, times its probability that is range, which is equal to pi 0 times p, which is equal to qp divided by 4 plus q. Okay. Now, so let's say, suppose p is 60%, then what is the probability that I get?
So if P is 0.6, then Q is equal to 0.4, and let us plug these values here.
0.4 divided by 0.4. So how much does this come to? 36 divided by 4.4. Right? So how much does this come to? This is 36 by 40. So this is 4 9 36 by 1. Yeah.
0.08.
Okay. 0.08. Okay. So which is something like 8%.
Yes.
Okay. So the probability of getting wet when the prediction is 60% rain is 8%. So this, yeah, this required a lot of conceptual understanding, but I hope this strengthened your idea of Markov chains.
Sir, it's wrong. It's wrong, sir.
Oh, it's wrong. Okay. Yeah, tell me.
Sir, 0.6 into 0.4 is 0.24. How it's 0.36?
Oh, yeah. Sorry. 0.24. Okay. Yes. So how much does it come to?
0.054.
0.054. Okay, good. So this comes to even smaller chances, something like 5.4%. Okay. Now, question is, okay, current estimate show, we did this, right? Current estimate show P equals 60% in Chennai. Okay, that's a lot of, thanks. So current estimate show that P is 60% in Chennai. We did that, okay. What is the probability of getting wet? We did that. Now, here's the modification. How many umbrellas should I have so that I follow the strategy above and probability I get wet is less than 0.1? Now, this is only getting harder, so please bear with me. But yeah, well.
So, but this probability does not depend on the number of the umbrella. The number of the umbrella is coming into the picture, or number of umbrella probably is coming into the picture as 4 plus in the denominator, I guess. That quantity is 4 here.
Very good observation. Yes.
So that we can put as a variable here and then put the values, and then we can find this thing.
Very good observation. Yes. So, yes. So, here you can see the pattern, right? 1 QP, QP, and so on. So, if you have more umbrellas, you can expect another QP term out here. Of course, you'll need to prove it using induction actually. Okay. But yeah, we don't have time to do that. But that is your hypothesis, right? And you get this QP, and furthermore, you realize that this is like pi 1, pi 2, pi 3, pi 4. If there are 5 umbrellas, you expect a pi 5 here. So if there are n umbrellas, if you have pi 5 equals pi 6 equals and so on till pi n, where n is the total number of umbrellas. And you do the same process, you substitute, then this 4 will become n, and therefore you will have n plus q, and then you'll have n plus q, and here you'll have n plus q, right? So yeah, that's a good catch. So let n be the total number of umbrellas. So according to the question, you have the probability of getting wet needs to be less than 1%, right? So probability of getting wet is less than 1%, which means that 1 by 100 is less than, probability of getting wet is less than 1 by. So probability of getting wet is less than probability of getting wet, of course. So, but which is equal to what? Which is equal to QP by N plus Q. Now solve this inequation. Can you find it out? By the way, P is 0.6. So you have 1 by 100 is greater than 0.6 times 0.4 divided by N plus 0.4.
Sir, is the answer is around 23.6? I mean around 24.
Yes, that's right.
Because you can't carry a partial umbrella, so 24.
Yes, N is greater than 23.6. Yes, that's right. And to make this integral 24. So if you want to make your chances of getting wet less than 1%, then you need to own a total of 24 umbrellas. And therefore, the chance of getting wet is very, very low. Okay, that's a lot of umbrellas. Okay, is this clear? Kishore, Goel?
Yes, this is clear to me. Yeah.
Okay, great. Yeah.
Yeah.
Okay.
And this number, I mean, I would be requiring a pretty large number of the umbrellas to make this probability zero. That I
Yes.
do not call. Yeah.
Yes. The more umbrellas you have, the more. Yeah. So yeah, that I mean, this is in terms of rain and so on, but you can apply this in some packet routing, things like that. Okay.
Sir, is it possible to get the absolute zero probability of being wet?
For that, exponential number of the umbrellas would be required. That is what I said. That this value n plus something becomes greater than zero would
That's a
mean
good
what?
point. So what
0.
would you mean?
So this one instead of 1 by 100, the value should be pretty large. Instead of 100, this value should be very, very large. So that becomes equals to 0. 1 by some infinite kind of the thing, that will become 0, right?
Yes. So
Okay,
n
that
needs
should
to
be
be
infinite.
infinite, no? So what you have is probability of getting wet is equal to 0, no? Or tends to 0. So then you need to have that which is equal to QP divided by N plus Q. Now this will be, now Q and P are fixed, so this will only be true when N tends to 0, the infinity. Okay. But so therefore, yeah. But so therefore you can rather ask like 0001, something like that, so that you have a more reasonable value of N. Okay. Right. Good. Okay, so yeah, that was one question. Okay, that took a lot of time. So the other question was about page ranking, but I mean the fact that we did this is the page ranking is becomes very simple. Okay. So let's do this quickly. We won't. I think like since you've seen this question number one, this becomes much more simpler. Okay. Consider a miniature web consisting of 3 pages A, B, C. Okay. And link structure is as follows: page A links to B and C, page B links to C, page C links to A. So this is how Google. This is a simplistic version of Google's page ranking algorithm. When you do a Google search, how does Google tell whether should I show page A first or should I show page B first and so on? How does it decide between that? Well, it uses this page ranking algorithm. Okay, and so so I have a page. Okay, and it has these links, and this is page A. Page A links to B and C, and B has a link to C, and C has a link to A. Okay. Now, question is, how does Google do this? Okay, so let's look at it as a graph. Okay. This is the graph, right? Corresponding graph G. Now, um, let's look at the adjacency matrix. So this is not a Markov chain yet. No? So let's look at the adjacency matrix. A, B, C, and A, B, C. So A maps to B with, A maps to B and A maps to C. B maps to C and C maps to A, and that's it, right? This is what we have. Now, can you think of how to make this into a Markov chain? Can you tell me, okay, can you tell me why this does not represent a Markov chain? Why does it not represent a probability matrix of a Markov chain?
Because this transition, the sum of the rows is not equals to 1.
Yes, right. So in a Markov chain, you cannot, you know, uh, you cannot move to two different states with probability 1 both. Okay, that will be against the spirit of Markov, how Markov chains work. So what you need to do is you need to do a normalization. Okay, so you need to normalize this. So what do you do in normalization? You will divide by the degree simply. So degree is 2. So turning it into a uniform distribution, in other words. Okay. Now is this a Markov chain?
Yes, yes.
Yes. So Markov chain, in other words, okay, are what are called row stochastic. So if you sum up the rows, you get 1. Okay. A fully stochastic would mean even the columns. Okay. Now the question is, how do you say, like, how do you rank the pages? Right? So here's a way to rank the pages, which like Google's page rank algorithm prefers ranking. Okay. Higher probability of entering some page, okay, or clicking into that page or entering some page would mean better ranking. Okay. So now again, the same question like before. How do I calculate the probability of entering these pages? Now I have a Markov chain. So what can I do?
What's the question?
So I need to. So here I have now come up with a ranking system. Okay, if and only if. So if I want a higher rank, how do I decide whether a page has a higher ranking or low ranking? I look at the probability that the user enters that page or not. Okay, the probability of entering those pages. Question is, how do I compute the probability of entering those pages given this Markov distribution? Markov chain.
Sir, using stationary distribution.
Yes. So stationary distribution measures the long-term probability of entering any state. Right? So so for example, if pi is my stationary distribution, what is the dimension of this?
1 into 3.
Yes, 1 into 3. 1 for each of the states. But what are the states? The pages. Right? Pi 1, pi 2, pi 3. So this is the probability of entering state 1 or page 1, page A, and so on. So I can even write it as page A, page B, page C. Good. So now can you compute the this stationary distribution of this matrix? This is Markov chain. Okay.
Yes, so then we can use the method we used earlier. So the pi matrix multiplied by the row stochastic, this transition matrix is equal to pi matrix only.
Yes.
And yeah.
Okay. And so therefore you have
Instead of
pi
1
C
1,
equals
this
pi
should have
A.
been half and half.
Yeah.
Instead of 1 1, they should have been half and half.
Oh yes, sorry. Good point. Sorry. Yes. So pi C is pi A, and pi A by 2. Oh wait, no. Oh yeah, that's right. Pi A by 2 is equal to pi B, right? And pi A by 2 plus pi B equals pi C, right?
Sir, what will happen if two pages are having the same probability or the same rank?
Two pages are having the same probability. Yes, that's what's happening here, no? I mean, from A going to B is half and going to C is half. They have the same probability,
Yes.
right? But I'll come to that. There are some nuances also. For example, what if some pages are unreachable, right?
Okay.
So what if there are no edges going to those pages? So these things are to be thought of, but I'll come to that point, which also like brings in like Goel's question that time. This is where I wanted to discuss about like whether a stationary distribution exists even or not. Okay, and furthermore we need to use this fact that pi A plus pi B plus pi C equals 1, right?
Sir, getting pi A as 2 by 5, pi B as 1 by 5, and pi C as 2 by 5.
Yes, correct. Pi A, pi B, pi C is 2 by 5.
1 by 5, 2 by 5.
That's correct. So what does it mean? So this is the stationary distribution. So what would be a valid ranking of the pages in order of their relevance?
A, C, B, or C, A, B.
Yes, either A, C, B or C, A, B. But in any case, page B is a bad page. I mean, it's the user has a lower probability of entering that. So therefore, I keep it in a lower priority. Okay, and so that's what the stationary distribution tells us. So this is the simplistic version of page ranking algorithm. You can even make this algorithm more complex by saying like some kind of machine learning updation. As the user clicks more and more, you add a bias to the Markov chain. You add more probability to this. Here we are working with uniform distribution, but it may not be that the user is um, uh, clicking each of these links with equal probability. But this why is this algorithm even used is because it takes very, very low space. You don't need to remember anything. I mean, that's the beauty of Markov chains. You just need to remember where you are currently. Very low space, very efficient in terms of space. Okay.
How can this be space efficient wherein there are billions of the pages and the dimension of the matrix would be billion cross billion? Even though the matrix would be very, very sparse, but still the dimension would be billion into billion.
So you will still have clusters. Okay. So there are these uh, edges going into a large cluster, and then these edges going into a large cluster. In that case, you can fragment matrix multiplication into tensor products. Okay, so tensor products is when you have a copy of several copy of matrices into another copy. You sort of blow up the entire piece. You There are techniques into doing this, and there are several techniques into doing this, and this is a field of what are called distributed algorithms. Okay, you have several servers. They are holding different parts of the data. They need to compute a function together. In this case, they are holding different parts of a matrix. Together, they need to compute the matrix multiplication. Right? So this is a very active field that is used everywhere. But I'm no expert in distributed algorithms. But you have these distributed algorithm schemes that are used to perform this.
Okay, yeah, all right.
Okay.
Thanks. Yeah.
Okay, good. So all good. Okay. Yeah, Kishore, everything fine? Okay, good. So, okay, that was a quick visit to page ranking. I think that was very simple considering the problem that we just solved in the beginning, right? So, now there are some very interesting questions, okay, but these are done in the lectures. Okay, these are to do with sampling. That is the next topic in this week, right? So, okay, actually, let me do the last question first. I think that's simpler. Okay, then I'll come to sampling those points because they anyway 3 and 4 they're already done in the lectures.
So that guarantee thing is not covered yet.
Oh,
That
yes. Thank you. Yes. Okay. So when a stationary distribution guaranteed to exist? Okay. It is guaranteed if uh, if there exists a k such that P to the K is not a null matrix, where P is the uh, matrix of the Markov chain, probability matrix of the Markov chain. Okay, and this property is called ergodicity. Now there is another alternate definition to ergodicity. Markov chain is ergodic if it is not regular. What did I say that time? What is the term for it?
Periodic.
Yeah, periodic is one of them. Okay, that time also I said regular. It's not regular. Irreducible. Yes, irreducible. And aperiodic. Yes. Okay, this is a simpler thing to explain. This is that all states reachable from every other state. Okay. For example, look at this Markov chain. So this is like 1. This was like half 1. No. There is always a path from A to C. There is always a path from C to A. There is a path from B to C. Because if there is something that cannot be reached, okay, if there are disconnected components, okay, if there are disconnected components, then I can never reach the stationary distribution, because now it will depend on where I start the Markov chain, whether I start from here or here, because my Markov chain will never escape these two different components. So of course the probability of entering these states will be different, no? Because for every state here in this Markov chain, the probability of entering into any of these states becomes 0. For every state in this Markov, in this component, the probability of entering into any of these states will be 0. Right? So it will depend on where I start with, which is against the spirit of stationary distribution. It should not depend on where you start with. Right? Now, the other thing is aperiodic. This is slightly nuanced, okay? Aperiodic means that as you run the Markov chain, let's say 1, 2, 3, 4, 5, and so on. Let's say first run, you land into states 1, 3, 4. And second run, you land into states 4, 5, 2. Third run is 1, 3, 4 again. Then what it means is, because you are still simply multiplying the same matrix over and over again, you get this. This is called a period. Your Markov chain is never going to stay in a single distribution. It's going to flip over and over again. This is called periodic. You want to avoid this. This is bad. This is periodic with a period of 2. So this is something you want to avoid. So this you don't want. So you want an aperiodic Markov chain. Now let me give you a shortcut. Okay, there's a shortcut theorem. I don't recall by whom. Okay, shortcut theorem for testing ergodicity. Because this is like this relies on like empirical runs, no? And this is also a very empirical thing that I keep powering. When do I stop? And check that it does not become a null matrix, right? So here's the shortcut theorem for testing ergodicity. That is, what was the theorem? So it was that if there exists two paths of different lengths, L1 and L2, two paths of different lengths, L1 and L2, such that GCD of L1 and L2 is equal to 1. So this is actually a stronger statement. If and only if Markov chain is ergodic. Okay, so all you need to do is look for two paths of different lengths, L1 and L2. So for example, yeah, go ahead, you're saying.
So two paths in between whom?
Oh yeah, sorry. So two paths of different lengths, L1, L2, two paths from any node U to V, okay, of length L1, okay, and it can be any UV, it's not for all UV, okay, that is enough, even that is enough. It's a very strong theorem statement. So for example, like I have a path A to B, B to C, which is a length 2. Another way to get to C is from A is A to C directly. So I have a path of length 1, I have a path of length 2. GCD of 2 comma 1 is equal to 1. So therefore this Markov chain is ergodic.
Oh, so does this the length of the path or the
Length
actual
of the
travel?
path. Length of the
Oh, I
path.
see.
Okay,
Oh, I see.
because definitely an edge means that it's a non-zero probability. That's all that matters. Okay.
Yeah, and because that the first property of the ergodicity, you said that irreducibility. It was
Irreducibility, it's enough just by looking at the connected components.
yes about the reachability. So irreducibility,
Sir,
reachability.
Yeah.
can you go to the page where you wrote this Markov chain is ergodic if it is irreducible aperiodic?
Oh yeah.
Before that, you
There I wrote regular. No, it should not be regular. This should be irreducible. Okay.
no, not this page. The last page where you wrote shortcut theorem, you
Oh
wrote a
yes.
points.
Hmm.
Yes, above that, if you scroll slightly above, Markov chain is even above that, the first line of
Ah.
some. When is stationary distance guaranteed to exist? Distribution guaranteed to exist.
Yes. It is guaranteed to exist if the Markov chain is ergodic. Okay. Okay. But the problem with this definition is like, how many times do I power the matrix? I need to keep checking whether it yields a non-null matrix. If it yields, good. But let's say I keep powering, I don't get null matrix, and I keep powering and powering. Right?
Within what's the meaning of that this thing is greater than 0? Does this mean that every entry of this PK is greater than 0?
Yes, because this is a null matrix. So definitely, in order to not get a null matrix, you need to eventually get a case. No, that's not necessary. greater than p, p and cross n is greater than 0 simply means that it's not a null matrix.
Oh, it has nothing to do with that semi-definiteness or that stuff.
What I
What is it?
believe
Matrix is positive definite or then semi positive definite, that sort of thing.
that's a good point.
So
Yeah,
because
this definition, this definition, okay, I'll confirm it. Okay.
but then my intuition here is since it has to do something with the reachability only, and the reachability would mean that in between any two nodes, if the value comes out to be positive, then we can reach to that vertex either directly or indirectly. Maybe.
Yeah, that's a good point. That's right. Yes.
So
So this means that there should exist a K where all the values are positive.
yes,
Yes, that's a good point. That's a good. Exactly captures irreducible. That's right. So this is not the null matrix. So why is it? Yeah, this is all values greater than 0. Okay, good. So
Could you
now,
show the shortcut theorem for once?
can you show the shortcut theorem? Sure. Just one
Shortcut.
moment. I'll charge my. Okay. Right. So yeah, let's quickly do this question. Okay. So it's about sampling. Okay. We are moving on to sampling. So what is sampling? Okay, sampling means you are given random access to parts of parts of a bigger object. Okay, and you are given limited access, random access to parts of a bigger object. What you are doing is you are trying to learn that object. You're trying to learn some properties of the object. Okay, it can be anything. For example, let's say you have a function. Okay, and the sample is like you're doing f. This is the kind of sample you are allowed, like for some x in say 0, 1 to the n. This is one example of a sample, and it can be like you have a set of numbers from 1 to m, and you are trying to sample with uniform probability. Sample a number n with uniform probability. So this is the concept of sampling. Okay, it's extremely helpful. It's extremely useful. Okay, and a good example is something called a secretary hire problem. Oh, I could have given this question. Maybe next time. So you need to choose secretaries, but you need to make your so there are candidates C1, C2, and so on, Cn, and you interview each one of them, and then you make you get some kind of score, S1, S2, and so on. But you need to make your decision right away. So if you don't, let's say there is a CK and you get the score SK, and you can't once it leaves, you can't say that, oh no, I want candidate CK once again. Okay, and so what is like the minimum number of interviews that you need to do, okay, so that you hire the best candidate with high probability. This is called a secretary hiring problem. It's an online sampling problem. Okay, and so I think you need the around 1/3. You need to sample like 1/3 of the. That's what I recall. Anyway, it's close to 1 by E. Okay, doesn't matter. That's not the question. This is the question. So let S be a region inside a unit square. You can sample points uniformly at random from 0, 1 whole square. Okay, between 0 and 1. Okay, so let's see. This is a grid, and you have a square. Okay, this is a unit square. Okay, this is a unit square. Now let S be a region inside the unit square. Can be arbitrarily shaped, but definitely each point will be like, x comma y. There are points, right? Infinitely many points, of course, right? You can sample points at random from, so you can sample points x, y at random from 0, 1 to the 0. So this points can be sampled only inside the square, right? Inside the square, maybe inside S or not. What you want to do is you want to build a randomized algorithm to estimate the area of S using n samples. Any idea how to do it?
So why this the shape of this S is irregular? Because we can have any number
The
between
shape
0
is
and
irrelevant. Okay, the shape is irrelevant in the sense that you don't already know what the shape is. Okay, but because then you would know the area. But what you can check is, okay, what is given for free to you is given for free is checking if x comma y belongs to S or not. Okay, this is given for free. You can check easily.
oh, I see. And X can have any value in between 0 and 1, any real value?
Any real variable.
Oh, I see. So this is like finding the area of jalebi.
Jalebi.
So yeah, of irregular shape. And this seems to me like Monte Carlo thing that people use.
Yes.
Something similar to that. So what we have to do that we need to find that which portion which points from this square lies in this region, say S. Percentage of the points which lies in this region S,
Huh.
and that will give an indication of the area of S.
Good. Yes. Good. Okay. Others? Any idea? But that's a good point about the percentage. So because it's already 7:52. So like Goel said, like if I sample any point, probability that that point is in S is equal to the total number of points in S divided by total number of points in square, right? But which is what? What is the total number of points in S? It is the area of S divided by total number of points in square is area of square, which is equal to area of S divided by area of square is 1 square, which is 1 because it's a unit square, right? So you already know now that, okay, if I sample, the probability with which I'll sample is exactly equal to the area of S, right? But I can't.
Sir, sir, here the equation is like favorable area by total area, and
Yes.
as
Okay.
there is total area is 1, it's already equals to the favorable area portion.
Yes, that's right. Now that is the probability, no? The probability is equal to the area, right? But how do you come up with the algorithm? Like in the algorithm, like how do you come up with probabilities? Right? What is the final quantity? How do you describe the algorithm?
So, like, I will find the expected value of this endpoints belonging to this. This S.
Yes.
Uh,
So how do I do it? I find the expected value, of course. Now the idea is that I'll define these random. Let me copy this diagram. Okay. Okay. Let me copy this diagram. Okay. So I'll set xi to be a random variable 1 or 0. 1 if the ith sample belongs to S and 0 otherwise. Okay. And the next thing I notice is, oh, probability of xi equals 1 is, as we saw, the area of S divided by 1 square, which is area of S. Right? Now, what do I, so now I want like a bigger random variable which will capture this xi, no? So what do we do? Usually we do summation xi, no? I equals 1 to n samples, right? And I do this. Now what do I do? Like Goel said, I'll calculate the expectation. What is expectation? Well, expectation is anyway going to distribute, no? By linearity of expectation, I have summation of expectation of all xi's by linearity of expectation. Right? I equals 1 to n. Now, but what is for a, since this is a binomial, binomial variable. Okay, it can be Bernoulli variable. It can be 0 or 1. That is, the expectation is equal to probability, right? We learned it a long time ago. So this is nothing but summation I equals 1 to n, where expectation is probability. So this is probability of xi equals 1. But what did we find? Probability of xi equals 1. It is exactly equal to area, which is equal to summation I equals 1 to n area of S, which is equal to what? I'm adding the same area. It is this does not depend on I, and I'm adding it n times, so n times area of S. So this is what I get, no, at the end. In fact, I can make the expectation equal to area by just saying that, okay, the random variable, I'll set it to 1 by n times this. So it will make it 1 by n times this, and this I can take it outside, 1 by n, and 1 by n, and 1 by n times, which is equal to.
So why to require this 1 by n? Because since x is, so every xi itself is Bernoulli. And so for the Bernoulli distribution, the overall expected value came out to be what? NP. No.
So it's just an extra thing. If you need not have done this. So what the final value you'll get is n times area, and you get expectation of x. So each time you calculate x, and you expect it to get closer and closer to the expectation, and then the expectation you expect it to be like n times area. So you will divide the final answer by n, and therefore you will get area. That too is totally fine. This is just a shortcut.
Sir, why do we have this 1 by n term?
Yeah,
Or,
exactly, Harshul. So we need not have this 1 by n term. Okay, so this is confusing, right? So let's not have it. No problem. Let's not have it. No problem. Okay, I'll explain why we have it also. Don't worry. So okay, this we have, right? So what do? You run, okay, sample. So here's the algorithm. Sample x comma y in 0 1 square n times. Okay, sample x comma y. Each time so let's say the samples, suppose whether they are inside S or not, answers are no, x1, x2, and so on. Let me write it as small x1, x2, so no, they are fixed now, x1, x2 to xn, right? And now what do you do? Find summation of x1. Okay, so I think this is only confusing. Let me write capital x1, x2, and so on. xn. Find x equals summation of xi's. Okay, and you get this. Last part is output what? X by n. Now the thing is, why? Because you made these samples, okay, which are supposedly the outputs of the random variables, because you sampling them uniformly at random, and you find x, this value. Now you expect for larger n, it will go closer and closer to the expectation. That's what expectation is. And you know that expectation is very close to area. I mean, expectation is n times area. So this x, okay, you expect it to be close to n times area. So therefore you will divide by n and then output, which will be exactly area of S. Right? So only I was just doing an additional optional trick, that is just that if I multiply with 1 by n here, then later I don't need to do this step. I can just output x directly, because this n is going to get cancelled off. That's all that I was doing. So no need to worry about that. Okay, so this is the final algorithm.
So What is the step number 2 here? Suppose answers are, so what
So
kind of,
what are the answers? These are exactly whether so let's say x sample xi yi xi yy in n times, okay, instead of saying n times, for all I in 1 to n. Okay, you take n samples, x1 y1 x2 y2 and so on. So xi says is equal to 1. It's the same definition. Xi is equal to 1 if and only if x1 y1 is an S. Okay,
yeah.
so this is fine. Harshul, you asked that question, no? So is that fine?
So
Yeah.
the last part, output you wrote x by n is proportional or
So
single?
so x by n is almost equal to n times area. Okay, so let me be explicit then. So this entire thing is almost equal to expectation for a large number, which is equal to n times area of S divided by n, which is equal to area. So output is close to area.
But then if I take only 10 samples, so then the value of the area will came out to be pretty small compared to the original one, and this is going to be a very
So you need to take larger and larger values of n to be more accurate. I mean, see, even if you take like 100 samples, you will get a pretty good estimation.
So will this technique work to compute the area of jalebi as well, and which has got many holes into it, and the shape is not irregular only, but then has got holes also.
Yeah, why not? Because the analysis will not change, no, if you see,
Right.
right?
Yes.
But like if S is very small, then you need to take more samples. That is true. Okay.
Yes.
Okay. Yeah, Harshul, this is clear?
Yes.
Okay, good. Now the final part of this question. Okay, I could not do the other sampling questions, but let's see if I can do it next time. Using this, describe how to estimate value of pi using random sampling. Can you? Yeah.
Please continue. So I need to say that inside the square, I need to consider the put the circle into it,
Yes. Good.
and then I can find this pi.
So computing pi. Okay. So now imagine you have a circle of radius r. Okay. You draw a unit square and you do a circle of radius r. Now what do you get? Well, you get again we computed that expected value of x is the area of S divided by the area of the square, right? I mean, the expectation is, and which is area of S by 1 square, right? And but this is also equal to the probability, like we saw. Probability that any point lies in circle, right? But what is this probability? This is the probability that number of points in circle divided by number of points outside circle, but inside the square. Okay. And also at the same time, what is the area of the circle? Okay, let me reduce the brightness. What is the area of the circle? This is pi r square, right? So, but okay. Oh, not number of points outside. So what I was saying, number of points inside the square, total number of outcomes, right? Points in square, right? Okay, good. So, okay. Sorry. Point in circle. This, rather than number of points in circle, I say the number of. So sorry, we are sampling as we go. No? So you'll get the answer this way. The number of points, number of points sampled in circle divided by total number of points sampled. This is what you will get on sampling, right? So you compute this every time. So you get pi r square is close to the number of points you find inside circle, okay, on sampling, n points, divided by n. And therefore you have, okay, where do I write? Therefore, pi is almost equal to uh, number of points inside circle on sampling divided by n r square.
We know the value of r square, that
Yes,
is.
because we are trying to compute pi. So the circle you can take as, whatever you want.
But then
So
the
therefore
radius
you
of the
can even take
circle
r
is
is 1, say. That's the best case. I mean, that's the easiest case. So number of points inside divided by n.
since we have taken the area of the square is equal to 1, so the value of the radius has to be half only.
Yeah, sorry. Then r can be at most half. So you can take maybe the square size is 2, but then your calculations will change. So maybe draw the circle whose radius is like less than half, something like that. But it's okay, right? But what that means is like, see, you can compute the value of pi yourself, right? You can like uh, stand, okay, and draw a 1 meter by 1 meter square and draw a circle of radius r, and then you can start throwing objects, right? Maybe you throw something that lands and does not roll, like a pen or a book or something like that, and you keep doing this. Each time you note down whether the circle landed in the how many tries you've done and whether it landed or not. Okay, and then
Sir,
you, yeah, divide by r square.
how did we manage to equate this area of S to that area of circle, sir? Because it could have been any shape from first part.
It could have been any shape, but this time I'm trying to compute pi. That's why I'm fixing this shape to be circle.
Okay.
Okay, so yeah, that's so in this second part of the question, it's not like the shape is already given to me. The task at hand is to compute pi, no matter how. I am free to come up with my own shape, whatever size, whatever shape. Okay.
Okay.
My objective is to compute pi, and that's all. So the idea is that I'll keep sampling points. Okay, I'll throw random darts. The number of points that land inside the circle divided by the total number of samples I throw times r square will give me a better and better estimate of pi. The more and more I take samples, the better and better value of pi I get. You can try this yourself physically. Like I said, you can draw this on the floor if you have time to do this, and you can start throwing things, and you can take this ratio. This is a way to experimentally find the value of pi. Right? Okay, good. So, okay, it's already 12 minutes past 8, so we won't be doing any more questions. These two questions are there. Um, I would say check out the lectures for 3 and 4. Both answers for these two questions are there in the lectures only. It's done exactly. Try to solve this bonus question. Okay, it's a very, very interesting question. Okay, we may or may not do it next time, but let's see. Okay, so that's all. So if you have any questions, you can stay back or you are free to leave. Okay?
Can you show the last part of that simulation of pi once?
Yes. Okay, here.
Yes, sir, this one. Inside circle and circle and points. Total number of points.
Yeah, thank you, Kishore. Yeah, see you next week.
Thank you so much. Bye.
Yeah, go on. See you next. Okay, bye bye. Good night.
Thank you, sir. Bye.
Okay, thank you, Sean. Yeah, thank you, Ankita. Bye.
Excuse me, sir.
Yeah, right. Bye.
Sir, throughout the course, I was finding a little difficulty in the topics and this subject only, sir. Sir,
Oh,
if you could suggest me something like this to pass the exam, and the date is also nearby only. Hardly 2 weeks are there for
okay. Oh,
preparing.
what is the date of the exam?
19 April.
19th April. Okay.
Sir.
So, this
What kind of sort of
yeah.
like?
This course
Mm,
is I agree. It's not a simple course. There are like a
yes,
lot
sir.
of topics in it that need to be conceptualized well. So I agree. It's completely normal. Don't worry about it. So
Throughout that, in today's lecture also, throughout I was just listening and observing, but still I was finding myself very below the sea.
oh yeah. The problems that I picked were also kind of harder than what you could expect in an assignment and exams. Now,
Hmm.
what I would say is, see, there is no other way than to solve problems yourself. Try your hand at solving problems. Okay. Now, what you should do is you should uh, find out like what the contents are in each week. What is the total, you know, and find problems. Okay, just Google for problems or ask ChatGPT for problems. Okay, in these areas, and you try to solve them yourself. And
Hmm.
if you can't do it, it's okay. You look at the solution, understand the solution, and then move on to the next problem. Okay, and you can check out the recorded videos also. These all these problem solving sessions are recorded, so you can look at them once again. Okay, and
So,
I see, since there is less time for the exams, I would have otherwise said like check out the book, but yeah, since there is very little time, like going through the book is it'll be too slow of a process.
Yes,
So
because there are two perspectives. Like one can be the learning can be done throughoutly. The second one is the scoring. Like,
yes, exactly. So right now, I think the scoring is something that matters more than the learning
yes, sir.
component, right? So
Yes, sir.
yes, right. So there is that's what I would say. Attend so in the coming problem sessions also make sure you attend it. Okay, ask me
Mhm.
if there are any problems. You can ask me if there are problems regarding previous week contents also. Okay, at the end of the lectures, I can talk to you about it. Right, we can discuss. The most
Yes.
important thing is like you've got the concepts well. How do you know you've got the concepts well? The only way is to actually solve more and more problems. Okay,
Mm. Mm. Yes, sir.
there is no other way to do it. Believe me. You can
And in the
hmm,
even in the examination also, will it be like the type of assignment which is given to us? The questions in the exams is similar to kind of assignments or the questions which are there in the lectures throughout. The lecture which you are taking, which should
uh,
be prioritized as
it's
if I
see
say.
it should be a mix, but you
Mm.
can expect questions there that are not too difficult. Also, you can expect. See the question papers are structured in such a way that
Mm.
if you've got the concepts clearly, then you should be able to attempt 70 to 80% of the questions with ease.
Mm.
Okay.
And the important topics for also the exam last the 7th week and 8th week, most of the weightage is more from the latest weeks end of the course now.
No. That's
Ah,
not necessary. In fact, it's better you build the good foundations in the beginning parts of the course so that you can move into more complex parts easily. Because see, uh, even like week 6, 7, 8, they all depend on the. For example, we talk about independent events,
mm,
right? Uniform distributions, things like that. They all
yes,
depend on good foundations in the previous weeks. So that is something that you need to build well. Okay, so
yes,
it's
sir.
okay. Don't. So just look at the main components of each of the lectures. Okay, no need to be bogged down. Okay, look at the main components and start solving questions. I would say uh, don't spend too much time. Okay, since there is less time, don't spend too much time in reading and learning about the theory right now.
Mm,
Just look
yes,
up problems, try to solve it. If you can't solve it, look at the solutions. And in the solutions, there'll be terms they'll use, there'll be concepts they'll use. Then look at the concept. A bottom-up approach instead of a top-down approach. Because if you start, that I'll learn the theory first, and then after all the concepts are built, then I'll solve problems. Then it might become too late because you enter this endless rabbit hole of preparation.
yes, sir. I
You
am
get it?
getting your point. Like while learning only, I have to try the numericals and put my own hands on rather than like
Yes.
jotting down the theory.
Yes, exactly. Start solving problems from the beginning itself. Start with simple problems. It's okay. Start with simple problems. If you can't do it, then look at the solution. Google the solution. Ask ChatGPT or Gemini, whatever. It'll now.
Yes,
I
sir.
mean, nowadays it's more than it explains you better than any teacher, right?
Mm,
so,
yes, sir.
uh, it'll explain to you, and then you can backtrack from there. You can ask like, oh, okay, so yeah, okay, so stationary distribution, what is it? And you Google it. Oh, ergodicity, what is it? And then you Google it, and then you backtrack. So since this is what I'm suggesting because you have lesser time, right? If you had lots of time, I would say, okay, do the theory first, learn all the concepts, and then solve.
Yes,
Okay.
sir. Yes, sir. Before talking to you, like I don't have a clarity and I was so confused like from where to start, what to do. But after talking to you, like yeah, I got a sight of a vision like what to do
Yes,
next.
yes,
Yeah.
yes, yes.
I
Take it
have a
slow. Don't worry.
kind
Yes.
of fun.
Okay,
Yes,
okay.
sir.
Yeah.
All
Don't panic. So is it you've mentioned it as a course for your college or something, college syllabus or something like that?
sir, actually, in my college, this is not my course, and in my college, the other subjects are done. I am in computer science only, and now my core subjects are going on from the computer science field.
Okay.
So
okay.
apart from my interest, I just want to explore something more out of
Oh, okay,
like
okay, okay. No, okay, okay. Then
as
then
an
it is.
additional, I am doing something out of my whole major
Oh,
stuff.
okay, okay, okay. Then it is okay. Then there is not too much at stake also, because sometimes colleges allow NPTEL courses to be
Yes, sir.
enrolled as courses, and then there is a huge pressure to score in these NPTEL exams.
So truly speaking, it is just kind of additional bonus for me only. If I score good, best for me. If I don't score good, or it's okay. It's just a new
Yeah,
needs for me.
yeah. Sure, sure, sure. But these concepts will help you in a long term, because probability stuff like this
Mm.
is used everywhere,
Yes,
right?
sir. Yes, sir.
Okay, okay. So you can let me know in the next discussion, or I can additionally I'll send you my email also. Okay,
Yes, sir.
so you can, if you have. Okay, so here's my email. So you
Uh,
can mail me. Okay, I will reply to you within 2 days at least. Okay,
I
at
mean,
most.
within 48 hours, like the customer care, they
Yeah,
once you
yeah.
raise a complaint in 48 hours, they.
Yes. I'll reply to you within 48 hours. Okay, but yeah, I may not guarantee that I'll immediately reply.
Oh,
Okay,
sure.
so yeah, so you can just hit me up.
That's a really good big lead. Thank you, sir.
Okay.
It was really a wonderful session, and thank you for the lecture, sir.
Thank you, Rajneesh. Okay, see you next week then. Okay,
Yes, sir. Yes. Okay. Bye.
okay, bye bye. Yeah,
Yes.
or should I? Yeah.
So, did you cover any problems on those distributions? Sir mentioned some of them: exponential, Poisson, geometrical distributions.
Yes, I had prepared questions for them, but I did not get to. Yeah, I had prepared a few questions for them, but I did not get to discuss it. But I also did not discuss it because uh, these questions are very formula based,
Okay,
right?
because I
So
think some of them are going to appear in the exam. Even assignment had one.
yes. Of course, don't skip them. But I'm just saying that these questions are very formula based. For example, if it's a Poisson distribution, then you need to. This is the formula for probability. This is the formula for expectation, and so on. So it's very formula based. So therefore, I didn't give it too much priority. Of course, it does not mean that if I have not covered it, it's not coming in the exams. Okay, please don't come
Okay,
in with
okay,
that
fine.
misconception.
Okay,
Study it. Okay, I just did not cover it because I held it in a lower priority, because I thought that students will be easily able to solve those kind of questions.
okay,
Okay,
fine.
okay,
Okay,
good.
bye. Sir.
Okay then, bye bye. Good night.